I will present to you my research project in which I apply for the very first time a framework called Learning to Reinforcement Learn to a problem known as Neural Architecture Search. I will start by introducing the Neural Architecture Search problem, followed by the highlights of my research so that we can state the conclusions. For this presentation, let's think only of neural networks for image classification. In this scenario, the setup is pretty straightforward. Given a dataset, we pass it to a neural network that is trained to identify the class of any image in the set. For the well-known datasets, for instance Cipher10, we already know some well-performing networks, such as DenseNet or ResNet. However, if we think of other datasets, the choice of the best network is not always obvious. That is the problem that Neural Architecture Search, or NAS, attempts to solve. The ultimate goal of NAS is ambitious. It tries to automate the creation of neural architectures for any dataset of interest. To accomplish this, researchers have investigated some popular methods, but my interest is in reinforcement learning because of its success on NAS in recent years. So far, NAS with RL has focused on finding a state-of-the-art architectures for Cipher10 only. But let's remember that the ultimate goal is to output an architecture for any dataset. If we were to apply the current methodologies to datasets other than Cipher10, we will encounter some impediments. In the first place, RL is a costly approach to NAS. One of the early groundbreaking works spent 28 days using 500 GPUs. More recent work has reduced this cost, for instance with 3 days with 32 GPUs, but still it is a high expense. Secondly, the standard form of RL requires us to train the agent from scratch for every new environment, since the policy learned is environment specific. Based on this observation, I formulate my research question. Is it possible to learn an adaptive strategy to design CNNs for image classification so that we can transfer it to avoid training from scratch? If this is possible, then we have two options that will help deliver architectures for arbitrary datasets. Number one, I could transfer the policy and use it as the initialization to train on new environments. Or number two, I could transfer the policy to new environments without training. I found that the answer to this question is affirmative, and I will show the methodology I used. Let's remember that the current NAS framework focuses on finding a state-of-the-art architecture for Cipher10. The differences I introduce are: first, to work with several datasets, so that the agent learns to design architectures for each of them. Second, the learned policy is adaptive, so it can be reused to design architectures for previously unseen datasets. Let's examine each of the components, starting with the reinforcement learning algorithm. I propose to use for the first time in NAS a deep meta reinforcement learning algorithm. I base it on the work of Wang et al., which is a modification of the standard advantage actor critique, or A2C. In short, it is an LSTM-based meta-learner that captures the relation between all the agent-environment interactions in an episode. The second element is a collection of datasets used to train and evaluate the algorithm. The agent interacts with 5 datasets from the metadataset, which have a shape of 84 x 64 with 3 channels. An essential characteristic of these datasets is that they all have a different level of hardness, which means that we expect different accuracies for each of them. The last element is the type of neural architectures that the agent can design. The search space, as it is known in NAS, it is based on the work of Xiong et al. We consider 6 types of layers, a maximum depth of 10 layers, and we train the architectures for 12 epochs to avoid expensive runs. The layers that we consider are on the screen. A special mention goes to the last layer, which can terminate the network at any time. For both the NAS elements and reinforcement learning algorithm, I have developed Python packages based on OpenAI components using TensorFlow. Now it is time to talk about the experiment and results. 2 experiments were conducted. The first one aims to study the behavior of the agent during training on the 3 environments: Omnigot, BBG Flower, and DTP. The second one seeks to examine the policy during evaluation. For the first experiment, we start by training the deep meta RL agent on the Omnigot environment, and we obtain a policy. For the second environment, we reuse the policy and train the agent again, so that we get a strengthened policy. For the 3 environment, we repeat. The result is one policy with knowledge from the 3 environments, We compare our method against a standard reinforcement learning baseline, specifically DQN. For this baseline, we train from scratch per environment because standard RL is not conceived to transfer the policy. The goal of this experiment is to evaluate the advantages of meta RL over the standard one. For this, I study the best reward per episode over time. We also want to see if the agent can adapt to every environment, and thus, I measure the policy entropy per environment, which relates to the exploration of the agent. Also, I compare the actions taken on each environment. Let's start with the results for the first environment. On the left, you can see the average reward every 50 episodes. In this environment, meta RL in blue does not outperform the baseline, which is in red. We also notice that the growth is slow. On the right, you can see that the average episode length every 50 episodes. For our networks, the episode length is equivalent to the depth of the network. As time progresses, both agents learn that deep networks perform better, which is something that we know from practice. In the second environment, the situation changes. The meta RL agent always outperforms the baseline. Since we transfer the policy, the episodes are longer from the beginning. We can see on the left that the knowledge developed by our agent in the omnigot environment leads to meaningful architectures for BGG Flower from the start, which is not the case for DQN. Also, the consistency of the meta RL approach is superior, meaning that the variance is lower than for DQN. This is an indicator for stable knowledge. In the third and hardest environment, meta RL continues performing better than the baseline. You may notice that the number of episodes differs between approaches. That is because meta RL builds deeper networks from the beginning, and thus the episodes are more prolonged, leading to fewer episodes. Still, during the time that both approaches coexist, our approach is superior and again shows less variance. These results suggest that deep meta RL gives an advantage over standard reinforcement learning when we transfer the policy. Now let's talk about the adaptation of the agent to each environment. In this plot, we see the policy entropy. High entropy relates to aggressive exploration. In the first environment, we notice that the agent explored more, and perhaps that's the reason why the best reward grows slowly. For the second one, the agent decreases exploration, but around the time step 12,000, it retakes it momentaneously. In the third environment, the hardest one of all three, the agent increases the amount of exploration, which is a good indication of adaptation. Finally, in this bar plot, we see the proportion of actions per environment. We observe that between the BGG Flower and DTD environments, there is a clear difference in the most important action. For BGG Flower, the most frequent action is the convolution with a kernel of 1, and for DTD is the max pooling with a pool size of 2. Also, the action related to the terminal state became more important for DTD than for the other two datasets, showing that the agent explored terminating the networks earlier than for the other two. We can say that the agent shows good signs of adaptation during training. For the sake of completeness, in this table you can see the running times per environment. All experiments use one GPU only. The second experiment is in two parts. In part A, the policy learned in experiment 1 is fixed, and the agent is challenged to design architectures for the two validation datasets. The goal is to see if the agent can deploy different strategies during evaluation. First, the results show that the agent is not able to improve its decision over time. The accuracies, however, seem meaningful and with small variance. For several birds, the behavior is similar. When we observe the actions taken by the agent, we see that it was not able to deploy different strategies. The distributions of actions taken on both datasets are roughly the same. A possible answer to this behavior is a short training. Again, the running times are on the screen. Now, let's remember that during reinforcement learning, the sampled networks are trained for 12 epochs only. For the part B of this experiment, the best two architectures per dataset are trained more intensively. We compare the performance of these two architectures against a shortened version of the popular BGG network, which is modified to match the input size of 84 times 84. The goal is to study the performance of the best designed architectures when compared to manually engineered ones. We see that the best architectures designed by the agent outperform the BGG-like network, particularly for the dataset CU birds. This helped to develop a notoriously better network. This shows the benefits of using our framework instead of manually engineering. It is time now for the conclusions. In this video, we saw that Deep Meta RL could outperform standard RL when the policy was transferred. We also saw that Meta RL agent could adapt to new environments during training without losing its effectiveness. However, we observed that during the evaluation, the agent could not adapt its strategy. Finally, we saw that the networks generated by our approach could outperform manually engineered architectures. This concludes the video. Thanks for watching.